All right, let's continue. So we're discussing content-based recommender systems. So the first question would be, what is the content? Right. For most content-based recommendation techniques, they were applied to recommending text documents. For example, the web pages or news group messages. Well, we will see why later. After we got the idea of how it works. So when we're discussing about text documents, the content of the items can also be represented as text documents. So basically the idea is to using textual descriptions for their basic characteristics. So there are mainly two types of data. One is structured, one is unstructured. So for structured data, it's usually presented as a table. Then in this scenario, each item is described by the same set of attributes. For example, in this table, these are different items, right? Item 1, 2, and 3. And these are the attributes. So these are the attributes. The title, genre, author, type, price, keywords, these are all attributes. So usually for the table, the column is the attributes and the row is to represent each and every items. And for unstructured data, we just take the free text as the description of that data or of that item. So there are two types of profiles that we are going to consider in content-based recommender systems. So one is item profile and one is user profile. For item profiles, for each item, we create an item profile. The profile is a set of features, and this set of features will eventually be converted into a vector or feature vector. For example, for movies, we can use the author, title, actor, director as its features. For text, we need to generate a set of important words in the document. So the question here would be for the text data or items, what is the important words, or how to pick important features. So usually we use the heuristic from text mining, right, to use TF-IDF to measure the importance of the words. So we have introduced this at the very beginning of this course. So if you're not, you can't remember it, I think it's in L2 or L3. Yeah, probably in L3. Yeah, in L3. So in this case, the document is the item, and the terms are the features. So for either way, the item profile will be a feature vector. Just remember this because we need this to create the user profile. So in order to generate the user profile, the most common way is to use the weighted average of rated item profiles. For example, if we, let's say for the user U, we have item V, let's see, VI, no, V1, V2, and V3. And we know because these items are the items that for the user U has already rated or purchased. So let's assume that each of them has a rate. For example, if we use a number between 0 and 1, so it could be 0.5. This is 0.7, for example. This is 0.2. And remember, for this v1, 2, and 3, they are feature vectors. And the features are the same for different vectors. Or say the dimensionality are the same, and for each dimension, for the same dimension from different vectors, they are essentially they're representing the same feature. Then the user profile, see the profile of the user is sum of only 3 of them, so I will write it down. So it would be 0.5 times v1 plus 0.7 times v2 plus 0.2 times v3, and you probably want to divide it by 3. Yeah, this divided by 3 is just to do a normalization. You can imagine if for another user u prime, if it has, say, 4 items that has been rated by it, then you are going to divide it by 4. Could be 6 or something. If you don't divide it by the number of items, then the profiling of the u prime would be much larger than the profiling of the user u. Also, you can't compare u prime with u using their profiles. Also, you cannot compare the profile of u prime with the item profiles. So that is the most common way to do it. And a variation would be weighted by difference from average rating of the item. Say still this example, but let's say, because let's assume that for each and every items here, we do have average rating. Right. So the idea is, for example, the rating for v3 is quite low. It's 0.2, right? But if the average rating of v3 is only 0.1, let's say, then 0.2 is not that bad. On the other hand, if the average rating of v2 is actually 1.0, then 0.7 is not very high. Right? So using average rating, using the difference from average rating actually represents. Now, actually, it helps to give a more to maintain the fairness between different items. Right? So as an example here, in this case, the profile of u would be because we're weighted by the difference of the average rating. So for v1, actually the difference is 0. So v1 does not affect the profile of u. And this is minus 0.3 times v2 plus 0.1 times v3 and divided by 3. So this is the variation of the user profile. How do we generate the user profile? And in order to do the prediction, so essentially what we're going to do is that we want to know whether the for a user X, for the user with user profile X and for the item with item profile I, should we recommend I to X? So this is based on the similarity between X and I. So in order to measure the similarity between two vectors, here we use their cosine. to measure their similarity. So for cosine, when these two items has their angle is 0, means they're quite similar, the cosine would be 1. Right? And if they're quite they're very different from each other, say the angle is pi, then the cosine value should be -1, which is the smallest possible value of cosine x and I. All right, so this is how we do the prediction, and all right, so say using this we can create a profile for each and every user, and also we can create the profile for each and every items. Then what we're going to do is, given the user u, we have different items. We compute cosine of u and vi, and we take the maximum vi we take this as the returned. So this is the first item that we should recommend to the user, unless it is already rated by the user. In that case, we would take the second one, the third one, and so on and so forth. So if we take a look at it again, the content-based recommender system, the first thing is to know what is the content, and to create profiles for items, and based on that we can create the profiles for users, and then we can compute the similarity or the distance between let me see, it should be the similarity between the user profile and the item profile to determine which item or items should be recommended to the user. So the good thing about content-based approach, there's no need for data on other users. Means all you need is the data from your own, because when you generate the item profiles, it is purely based on the item itself, and when you generate the user profile, it's purely on the user's rating of the items. It only relies on the ratings that for these items that are from the specific user. It does not need any data from other users. So even you got only one user, you can still use this approach and recommend items to that user. It is able to recommend to users with a unique taste, because it fully takes consideration of the user's rating of the items, right? So if the user like some items, then the weight would be higher. If the user does not like some items, then the corresponding weight would be smaller. Right? So it actually can suit different users with different tastes. It is able to recommend new and unpopular items because for the item, when we need to compute the item profile, we only based on the item itself. So you can imagine that, for example, the user really likes item V1, and which means cosine u V1 is very large, say larger than 0.9, right? And if we have V2, and we know that V1 and V2 are quite similar, although V2 is new, but we still can create the profile of V2. And say if we assume that the cosine between V1 and V2 are 0.9 as well, right? then you can imagine that the cosine similarity between U and V2 would not be small. Actually, you can compute it, but I will skip that for today's course. So it is able to provide explanations because we have created the user profile and the item profile. So in order to provide explanations of recommend items, we can just by listing the content features that caused an item to be recommended. Now, these are the good things about content-based approach, but for the bad things about content-based approach, there are several as well. So first one is that we need to find the appropriate features, and which is hard for some types or for some data types. For example, for images or movies or music, or either the features are too few. For example, for movies, if we only have actors, directors, let's say the title, it is not enough. It is not enough. And for images, it can be worse, especially when we don't have neural networks. So now, since we have neural networks, everything can be represented by a high dimensional vector. It becomes much better than before, but still, I mean, it is not that intuitive to using feature vectors to represent these data types for recommendation systems. That's why, if you still remember, we have mentioned here that are applied to text documents because it is nature to use TF-IDF or even count vectors to represent the characteristics of text documents. So this is the first bad thing, and for the for the recommendation for the new users, we can do nothing if we use a content-based approach, because the new user did not rate anything. Right? Well, I don't know how many of you are Quora users. Right? Quora, I guess. Yeah. So the first time when I registered in Quora, it actually showed me a list. Let me to tick at least 10 topics that I would be interested in. Right. My guess is that they are actually using this to initialize a user profile for me. Right, because it kind of forced me to tick at least 10 topics or 10 items, right, so they can have a user profile. Otherwise, I mean, if they don't ask me to do this, they don't know what to recommend to me. Well, they can still recommend some popular articles to me, but that is totally not customized, right? So that is the bad thing of using content-based approach when we facing a new user. And it is the over specialization problem is that it never recommends items outside the user's content profile. For example, let's say I bought books online, right? And if I only bought books that say regarding computer science, let's say, but I've never bought any books about fiction. But let's say I'm indeed a fan of science fiction, for example, but somehow I never bought a book online about science fiction. Right? So the problem is that the system does not know that I am a fan of fiction. It only knows that it seems that I am a fan of computer science books. Right? But people do have multiple interests, just like me in that example. So the system is over specialized me. Right? It never considered I could have other interests. Right? Also, it is unable to exploit quality judgments of other users because it only focuses on the user profile for that specific user. It does not make use of the information or the judgments from other users. So this actually motivates the idea of collaborative filtering. So the collaborative filtering, the main idea, if we conclude it into one sentence, is that show me more items favored by others who have similar tastes with me. So you can think of it focus more on a taste of the users, and more importantly, other users, not the user itself. So collaborative filtering is the most prominent approach to generate recommendations. It is used by large commercial e-commerce sites. It is well understood, and we have various algorithms and various exits. So it is applicable in many domains. For example, books or movies, music as well. And the approach essentially uses the wisdom of the crowd to recommend items. So it's trying to find people or users who has the same or similar tastes as you, and based on their rating, to predict your rating for those items. So the basic assumption and the idea of collaborative filtering is that the users gave ratings to catalog items implicitly or explicitly. For example, they can rate the items, gave us a score or star to the items, or it can be obtained from their purchase log or their click log or something. And customers who had similar tastes in the past will have similar tastes in the future. So the tastes of the customers or the users will remain the same. It will not change drastically. So these are the basic assumptions of collaborative filtering. So the workflow of collaborative filtering, or here we use a simple figure to show the workflow. So basically, we first consider user X, who is Mr. A here. So we compute Mr. A's preference to the system. We compute Mr. A's preference and show it to the system. Then for the second stage, we find a set N of other users whose ratings are similar to X's ratings. Right? So here we do a database search. We search from the database to find the users that having similar preference as Mr. A. Right? And the third stage is to estimate X's ratings based on the ratings of users in N. Right? So this is N. This is X. Now the third stage is to do the recommendation. We from these users, from the ratings of from these users, we can estimate X ratings and do the recommendation. So the idea or the workflow of collaborative filtering is as simple as this. So user-based nearest neighbor collaborative filtering. So we start from this kind of simple example first, or algorithm first. So the basic technique here is given an active user and an item I that is not yet seen by the active user. What we are going to do is we need to find a set of users, right, and who liked the same items as Alice in the past, and who have rated item I. So there are two conditions. One is they liked the same items as Alice, and the second is they have rated item I. Otherwise, I mean, we cannot get enough information regarding item I. And then we use the average of their ratings to predict if Alice will like the item I or not. And we do this for all items Alice has not seen and recommend the best rated. So the idea is quite simple. We find a set of users, right, and we, based on their ratings of item I, we estimate the Alice rating of item I, and we do this for all the items, and then we can recommend the best rated. So the basic assumption and idea of this collaborative filtering algorithm is that if user has similar tastes in the past, they will have similar tastes in the future. We have mentioned this before. Users' preferences remain stable and consistent over time. So this is because we're considering it's like in the data stream, right? So the data, like in the data stream, what Alice used to like should be consistent over time. I mean, for in the future, Alice would also be like these items. Otherwise, it is meaningless to find those users liked the same items as Alice, because Alice's tastes could change, these users' tastes could change. So there is no there's no point that we can use this to estimate Alice's rating for item I. So let's look at an example here. So basically, we have a database of ratings of the current user. So these are the users, and for these are the items, and these are the rating. These are the rating, and we don't know this one. This one is what we want to estimate. Now we want to determine whether Alice will like or dislike item 5, which item Alice has not yet rated or seen. So in order to do that, there are some first questions we need to consider about, like how do we measure the similarity? Right? We want to find the users that have similar tastes as Alice, but what is a similar taste? What do we use to measure the similarity? And how many neighbors should we consider? Right? Because these neighbors, although they have different, similarity to Alice, but which one or which neighbors should we consider? Like, should we only consider the most similar one to Alice, or should we consider the most k similar users to Alice, or let's say we consider those users that has the taste that the similarity of the tastes to Alice is above a certain threshold, right? So we need to decide that as well. And also, how do we generate a prediction? How do we generate a prediction from the neighbors' ratings? Right? Given the neighbors' ratings, how do we generate the prediction? So the first thing is to find similar users, or how to find similar users. Now let Rx be the vector of user X's rating. Right? For example, here is actually the rating. It means the rating is 1, 1, and 3, and this 2 is unknown. Right? So for Ry is another user's ratings. Right? So this is 1, 2, and 2, and this is these 2 are unknown. And there are several similarity measurements that we can use here. Including a Jaccard similarity, cosine similarity, and Pearson correlation coefficient. Yeah, I probably should put this before LSH, right? So you can have a better understanding of why do we need to discuss that many different similarity and distance functions. But anyway, I mean, for Jaccard similarity, what we measure is the size of the intersection between Rx and Ry over the size of the union of Rx and Ry. In this case, we treated Rx and Ry as sets. So it would be Rx is 1, 4, 5, because Rx only rated the first, fourth, and fifth item in all these 5 items. Right. And Ry, it rates only the first, third, and fourth items. Right. So if we treated Rx and Ry as sets, we can only represent them as this. So obviously the problem is that we kind of ignore the value of the rating. Right. We only maintain the information that did the user rate what items has the user rated. Now for cosine similarity measure, the similarity is the cosine. The similarity is the cosine value of the angle between Rx and Ry. In this case, we need to represent Rx and Ry as points or vectors. So in order to do that, we use the rating as it is, and we use 0 to represent the item that has not been rated. So Rx equals to 10013, as you can see here. Ry equals to 10220. So the angle between Rx and Ry, the cosine of that value, that angle would be the cosine similarity. But the problem here is that they actually treat missing ratings as negative. What does it mean? Because the cosine of Rx and Ry essentially equals to the inner product of Rx and Ry over divided by the norm of Rx and then divided by the norm of Ry. Now, if we consider the inner product of Rx and Ry, it would be, in this example, it would be 1 times 1 plus 0 plus 0 times 2 plus 1 times 2 plus 3 times 0. Now, whenever we have a 0 here, no matter how large this 3 would be, this one would be 0. So the missing values, the missing ratings from both x and y does nothing, or does not contribute to the cosine value of Rx and Ry at all. So this is the problem of cosine similarity measure. Now let's consider the Pearson correlation coefficient. Here we first define SXY is the items rated by both users X and Y. So it is essential the intersection of Rx and Ry in Jaccard similarity. When we treat them as sets. And we use Rx bar and Ry bar as the average rating of X and Y. So in order to compute the similarity between x and y, we firstly consider for each s in Sxy. So for each item that is rated by both users x and y, we use the rate of s in x minus the average rating of x times the rate of s in y minus the average rating of y, and divide. So we do the sum over all the items that is rated by both x and y, and we divided this by the square sum of the difference between items rated between the item rate and the average rating of x. So of those items that is rated by both users and x and y, and we do the same for y. So in this example, we have Sxy equals to 1 and 4, right? And we can compute Rx bar and Ry bar. Note that when we compute the Rx bar and Ry bar, the average rating is over Sxy. It's over Sxy. So in this case, it would be Rx bar actually equals to 1, and Ry bar actually equals to 1.5. 1.5. Then for each s in Sxy, let's consider the first item first. So 1 minus Rx bar, which is 0. So no matter what this part is, it's a 0. Plus another, it's also 1. It's also 1 minus 1 is 0. So 2, 0 plus together is still 0. So we don't need to compute this part. The similarity of x and y is actually 0. It's actually 0. So this is a Pearson correlation coefficient. Let's have a detailed looking at this different similarity matrix. So say this is the users. These are the users, and these are the items. In this example, intuitively we want similarity A and B larger than similarity of A and C, because as you can see, for A and B we have although they only shared item between A and B is HP1, but the rate is quite similar. For A and C, they actually share 2 items, but the score are quite different. But for Jaccard similarity, as you can imagine, so here the intersection is 1, union is 5, so it's 1 over 5, and here the union is 4 and intersection is 2, is 2 over 4. So for Jaccard similarity, we actually got similarity between A and B smaller than similarity between A and C. And for cosine similarity, if you do the computation for A, B, and you do the computation for similarity between A and B and A and C, you would have that A and B is slightly larger than A and C. And since we have mentioned before, the cosine similarity actually essentially considers missing ratings as negative. So the solution would be, one of the solution would be subtract the row mean. So if we do that, we would have the new matrix like this. So for example, the row mean for row A would be 10 over 3. This would be 14 over 3, and this would be 12 over 3. And if we subtract each item with the row mean, we would have something like here what we've got. And if we compute the similarity between A and B versus A and C, on this new matrix, we would like this answer. So the differences would be larger. The difference between these two similarities would be larger. But if we look at the Pearson correlation, which is a popular similarity measure in user-based collaborative filtering, the possible similarity values are between -1 and 1. So first of all, for SXY, it is 1, 2, 3, 4 items. For Alice, if we fix X as Alice, Y is user 1, 2, 3, 4. The SXY is always 1, 2, 3, 4. And if we compute the RX bar and RY bar so the average rating scores for these 5 rows, it's actually 4 here. This should be 9/4. This is 7/2, and 3, and this one is 13/4. So if we compute, we can actually pre-compute RXS minus RX bar, and also for all X in Alice user 1, 2, 3, 4. Remember, when we compute the average score, we don't include the item 5. We don't include item 5. Then if we do the subtraction, we would have this is 1 minus 1, 0, 0, and here should be 3/4. This is minus 5/4, minus 1/4, and 3/4. We can do all the rest, as you can see in the red. So it's kind of easy to see that the similarity between Alice and user 2, because this is 0.5 plus minus 0.5, which is 0, plus 2 zeros, so the similarity would be 0 here. And here is also if you multiply the numbers, the corresponding numbers or ratings here, you would have the sum would be 0 again. So this 2 would be 0. Now let's look at the last one, for example. So we first compute this part. So it would be minus 9/4 plus minus 7/4, which is minus 4. We don't have the last two. We don't include items 3 and 4 because for Alice the value is 0. And then we compute this part. So this one would be square root of 1 plus 1 plus 0 plus 0 would be square root of 2. And for this part, we compute it here. It would be the square root of, say, 81 plus 49 plus 25. Eventually, it would be equals to 204/16, which is then if we do the computation, we would eventually get this number, minus 79. All right. So this is how do we compute the Pearson correlation similarity. Right. Now let's look at the second question. What would be rating prediction? Now previously we have found those similar users to the user X. Right. So the next thing would be, how do we predict the rating of the unknown item of user X? So let Rx be the vector of user X's rating, and let N be the set of K users most similar to X who have rated item I. Then we need to do the prediction for item S of user X. We can use the average or the mean of the ratings of item X among all the users in N, right? And also we can take the similarity between user X and user Y into consideration, and use this similarity as a weight. Right? So it's kind of like a weighted average of the users of the rated item I from the users in N. Right? And also we may have other options, and we have many other tricks that is possible to be applied here, but due to the time limitation, we won't introduce them in this course. But if you are interested, I mean, there are plenty of resources to read. So user-based collaborative filtering is said to be memory-based. So essentially, the rating matrix is directly used to find neighbors and make predictions. And the rating matrix need to be fit or stored in the memory, because we need to do computation over it. And it does not scale for most real-world scenarios, because the large e-commerce sites have, let's say, tens of millions of customers, so the users, and millions of items, at least. Actually, the number could be much larger. Therefore, sometimes we consider model-based approaches where they are based on an offline pre-processing or model learning phase. So the model is learned to do the prediction, whether, say, the prediction is whether the item should the model is learned to predict the rating of of a specific item for a specific user, right? So the model is pre-trained. So at runtime, we only need the learned model, and we use it to make predictions. Right? So at runtime, it's like we will apply the learned model with the input of a user and different items, and do the prediction, and take those items with highest value or highest predicted ratings as the results, or as those to be recommended to the user. All right. So the models are updated or retrained periodically, and in order to achieve such kind of model-based approach, we have a large variety of techniques can be used. Although the model building and updating can be, especially updating, can be computationally expensive, but the updating is essential, because you can imagine for this kind of recommendation systems, the number of customers and the number of items are increasing rapidly every day. So it is very important for us to update the model periodically, usually say once per day, right? For many e-commerce sites, and also, I mean, because it is a machine learning model, so rather than updating it, usually we just retrain it and train such a model. Because we have so many customers and so many items, the training time would be very large, right? So that's why we say the model building and updating can be computationally expensive. So that's pretty much all for user-based collaborative filtering, and also for today's lecture. On Wednesday, we will discuss other collaborative filtering methods or approaches. For example, the item CF, right? And then we will kind of finish all the contents of this course. All right, so that's all for today. I see you on Wednesday.